All right. Unit 2, assignment 10, pretest, like part 2 or whatever. This is for the calculator section, which will actually be the first part of the test, but it's the second assignment, so whatever. So we're using a calculator on here. There will be radians and degrees, but mostly degrees. And then the regression problem is definitely radians. But on here, you could show a little bit of work, because if you're like me, you don't want to search for a secant function. It's probably quicker to just do 1 over cosine. So maybe write that down if that's your strategy, just in case something goes wrong. Then I know that. Now let's see, let's make sure we got to be in degree mode, or we could add the degree symbols. It's up to you, but there it is, 3 decimal accuracy, 1.140. I'd write the 0. That at least communicates your intention. And then cosecant is 1 over sine of pi over 6. Now, this is one we don't even need a calculator for. I mean, you can use a calculator, but sine pi over 6 is 1/2. So the answer is 2. But you could use your calculator and go to radian mode and do 1 divided by sine pi over 6. There you go. There's the answer. Might be quicker to do it without a calculator. Next one, let's go back to degree mode. And cotangent is going to be 1 over tangent. Now, if I were doing it without a calculator, I would change it to sine and cosine. But I have a calculator, and I think it's definitely worth it to use your calculator here because of the minutes and seconds. Your calculator has the ability to do that. So let's see, 1 divided by tangent of 32. Go to the angle menu, degrees, 5, go to the angle menu, minutes, 18, go alpha plus, and there's your answer. 3 decimal accuracy, 1.594 or 1.595. The others so far, round truncated, turned out to be the same. So there you go. Okay. We also are solving triangles with our calculators. This is not one of the common angles that we memorize, so we're going to need to use our calculator to do it. So I would say, well, this is going to be quadrant 2 and 3 because it's negative. I'm going to ignore the negative to find alpha. So inverse cosine of positive 1/3 is going to give me what alpha is. Usually, on those other problems, we just do that in our head. So we should be in degree mode, which we are. Just double check degree mode. Okay, so we're going to do inverse cosine of 1/3. I'll write that down with more than 3 decimal accuracy, 70.528779 degrees. So to find the different answers, theta equals quadrant 2 is going to be 180 minus alpha. So 180 minus alpha, 180 minus previous answer. So it's going to be 109.471220 plus 360K. And then so that's quadrant 2. Quadrant 3 is going to be 180 plus alpha. So 180 plus 70.5287737, 250.5287779 plus 360K is all the possible answers. So I'm doing this just like I do ones without a calculator. Now, I just want the answers from 0 to 360, so that means we just want 109.471 degrees and 250.528 degrees. Now, you could do 250.529 if you want to round. First one's the same, rounded or truncated. There you go. Okay, cosecant is the same as 1 over sine, so that's the first thing I would do. And then I would change it to sine equals -1/4, flip both sides. And then I'd say, okay, well, that's quadrants 3 and 4 because it's negative. And then I'm going to do alpha equals inverse sine of +1/4. Figure that out. So inverse sine of 1/4 should give you an angle between 0 and 90 alpha. I feel like it's just way easier to work with. So then quadrant 3 is going to be theta equals 180 plus alpha. Quadrant 4 is going to be theta equals 360 minus alpha. So 180 plus alpha is 194.4775122 plus 360k. And 360 minus 14.477512219 is 345.522487 plus 360k. I just want the answers between 0 and 360. So it's just going to be 194.477 degrees and 345.522 degrees. Those are the truncated answers. Rounded, this one would be 194.478. The other one would stay the same though. Okay, secant is 1 over cosine. I'm going to change it to cosine. And so that's going to be quadrants 2 and 3 that are negative. Alpha is going to equal inverse cosine of +1 over 3.7. So inverse cosine of 1 over 3.7 is 74.319649. Now label your stuff, right? Quadrants and alpha and stuff like that. So quadrant 2 is going to be 180 minus alpha, and quadrant 3 is going to be 180 plus alpha. So 180 minus the previous answer is 105.680350 plus 360k. And 180 plus 74.319649.7 is 254.319649 plus 360k. And so my answers for theta are 105.680 degrees and 254.319 degrees. 3 decimal actually truncated. If you rounded, it would only change the second one. So there you go. Some solving kind of simple trig equations with the calculator. Now, here we have a problem with a bunch of different pictures. Okay, so I think the best strategy here is just try and find as much stuff as you can. Now we know FE is parallel to CD is parallel to AD, parallel parallel. EC is 40. So if this is 20 and this is 90, then this is 70. This has to be 20. This has to be 20. Alternate interior, of course. I can't remember the name for those. Vertical angles or something like that. This would be 160 because I have to 180, 160, 175. This would have to be 5. This whole thing here would be 20. This would be 15. This would be 75. This would be 160. So I'm just trying to find all the angles. So with that in mind, we're trying to find AC. So AC is right here. AC is the hypotenuse of this triangle. So we can use well, this is what we know over here. So maybe we have to find something before that. We got to find a side that connects to a triangle that has AC as a side. So we could look at this triangle right here. We could find this side right here. So that would be, you have a variety of ways to do it. I would do tangent of 70 equals opposite over adjacent. This is just one way to do it. So then x equals 40 tangent 70 degrees, which we could get a decimal for. I don't know if I want to get a decimal yet. I mean, I might try and keep it exact, but we'll just write it down right now, 109.899096. So then we could use that side to help us find AC because it's this non-right triangle right here. So I'm going to start with law signs. Sine of 160 over AC, which is what we're looking for, right? Equals sine of 5 degrees over x, right? Or DC, or whatever you want to call it. And then equals sine of 15 degrees over AD. Now, I'm just going to stick with these right here. So that means if we're trying to find AC equal, we could flip both sides. And then we could solve for AC. So AC equals x times sine of 160 over sine of 5 degrees. So exactly, if you want to keep it exact, we could say 40 tangent 70, because that's what x was, sine 160 over sine of 5 degrees. So then AC equals, as a decimal, well, we already have that part right there, right? So then sine of 160 times sine of 160, previous answer times sine of 160 divided by sine of 5 equals 431.270546. Just in case I need this for another calculation, I'm going to keep some extra decimals right now. Okay, so that's AC. EB. Let's see, where is EB? EB is this whole thing. So we got to figure out what this is before we can find EB. AB is right here. We now have AC right here, 431.270546. So we could start working with this right triangle here, which is a little simpler than law signs, all cosines, to find that. That'll help us find that and find that. So I'm probably just go with basic trig and say, okay, well, let's find this side over here. I'll call it y for right now or something, just use it variable. So I'd say, okay, well, opposite over hypotenuse, that'd be sine. Sine of 15 degrees equals opposite over hypotenuse. Now at this point, I'm just going to go ahead and use the decimal because, I don't know, it's pretty complicated. We could keep using this if you want, but it's getting So then y equals either 431.270546 sine of 15, or we could go ahead and put the exact version would be this whole thing right here, right? 40 tangent 70 sine of 160 sine of 15 all over sine of 5. But this is going to be BC. So we could just take this answer from the previous step and multiply it times sine of 15. And so that's 111.62103111. So this is one of our answers. And then EB would be 40 plus y, right? So we just add 40 to that. So we get 151.62103111. That's going to be EB. So AC is 431.270 or 431.271. Are there any units? No. And then EB is 151.621. Round truncated comes the same. And then AB is this side right here. So I'm going to call that Z or something. So we could just use that previous value and say, okay, well, cosine of 15 degrees equals adjacent over hypotenuse. So then Z equals 431.270546 cosine of 15. And so 431.2705468 times cosine of 15 equals 416.575359. So here it's going to be 416.575. Round truncated comes out the same. So there you go. All right. Tree and hill. Oh, yeah. You guys ready for this? The test? I told you. I guarantee there's going to be a problem kind of like this. So we got to get a good picture. And the bigger the picture, the better probably. So I'm going to try and make this picture, hopefully, as big as I can, because it's going to get messy. So we have a tree on a hill. They go straight up, perpendicular to the horizontal. Vertical tree stands on a hill, slope incline 8%. So that's this angle, 8% slope. The angle of elevation is 20. I'm going to wait to put that. That'll be the last thing to put it. The shadow of the tree down the hill, right? Shadow of the tree down the hill is 60 feet. So this is 60 feet. Okay. Find the height of the tree. So we're trying to find this. Now, after I draw the shadow, I'm going to connect this shadow on the tip of the tree to the sun. And then I can draw a horizontal of the sun and get the angle of elevation or angle of depression of the sun. This is 20 degrees right there. Okay, so then I'm going to draw horizontals at all the intersections, all the corners of the triangle, because we're going to get a bunch of parallel lines with transversals. So if that's 20, this is 20, this is 20. This whole thing here is 20. This is 8 though right here. So this is going to leave you with 12 degrees inside the triangle. This is 90. This is 8. This is 8. Anything tied to the slope, you're getting those parallel lines that are related to the 8 degrees. This is 8. This is 8. That's 8. Right? Alternate interior angles. This would have to be 90 altogether, which makes this 70. So I think I have a pretty good picture here. Now I'm going to redraw it with just the triangle because I feel like that would be helpful. This was just to work everything out. This is 70. This is what we're trying to find. This is 60. If that's 8 and that's 90, this is 98. And this was 12. So that's a simplified version of our triangle, just with the crucial stuff. So this is a non-right triangle, so we're going to try and use law. I'm going to start with law of sines. Well, what kind of situation do we have? We have the H doesn't count as one of the known information. So we have angle, side, angle, or you have angle, angle, side. So there should be one unique solution. So I'm going to start with law of sines. Sine of 12 over h equals sine of, I'm trying to use the ones that are tied to what I know, what I'm looking for. Sine of 70 over 60 equals sine of, you could do 98, but you don't know that and you're not looking for it. So I think this is good enough, right? We could solve for h, there's only one unknown, and we put those together. So you could flip both sides and then multiply both sides by sine 12. So try and keep this exact as long as possible, which is pretty reasonable this time. And then we're going to get our answer. So 60 sine of 12, close parentheses, divided by sine of 70, close parentheses, equals 13.2753, which is kind of weird. It cuts off. Is that exact? I don't know. It's kind of weird. So h equals 13.275. Round truncated comes out the same. What are the units? Definitely units on this problem. This is feet. Okay, there you go. Next one says find the height of the tree if the shadow's up the hill. Well, that's a new picture. I mean, I don't want to add anything to that picture, so let's draw a new picture. A lot of the information is the same. You have 8-degree slope. You have your tree. But now the shadow is going up the hill, which changes everything. So that means the sun has to be over here. Now the angle of elevation of the sun must be the same. Depression, 20 degrees. Trying to find the high tree. The length of the shadow is still 60 feet. So we're going to draw horizontals at each of the corners of the triangle to form all special pairs of angles and parallel lines. So if that's 20, this is 20, this is 20, this is 20 right there. If that's 8, this is 8, this is 8, this is 8, this is 8. Okay, so that forms 90 degrees. If that's 8, that means there's 82 degrees left inside the triangle. If that's 20, these form 90 degrees, then that means there's 70 here. This is 20 and this is 8, so altogether that's 28. So I'm going to redraw my triangle. Say, okay, well, it's 82, 70, 28, 60 feet, and h. So what kind of triangle situation do we have here? We have a angle side angle, or angle side, not side angle side, but should get one unique solution. Don't have to worry about two solutions. Don't have to worry about any of that stuff. So I'm going to start with law of sines. Sine of 28 degrees over h equals sine of 70 degrees over 60 equals sine of 82 over, don't know. This is good enough. Flip both sides. And by the way, you could set up law of sines upside down from the way we usually do it. That's totally okay as long as you're consistent. So h equals 60 sine of 28 degrees over sine of 70 degrees. And then on your calculator, it's going to be 60 sine of 28 closed divided by sine of 70 closed. 29.976072. So h equals 29.976 rounded truncated, comes up the same. I need units, feet. If you don't put units, losing points every time. So there you go, little solving triangle action there. But there could be some other solving triangle problems on the test. The ASS situation could come up where you got to check for two solutions and all that kind of stuff. The whole finding the smallest angle first issue can come up. So on the back, we have a couple more problems here. Let's see. So we know that M and N are parallel. We want to find AC and angle ACB. ACB. Now, ACB would be an angle that's not even drawn on in here yet. We're trying to find that. This is 100. That's 50. AC is also, yeah, so AC is also that length right there that we're trying to find. So let's see, if this is 112, then this is 78, and this is 78, and this is 128 altogether. I don't know if we know these angles. I don't know if we can, we can maybe figure them out at some point. You know what? This is supposed to be 68. So this is supposed to be 68. So this would be 118. I made a little mistake there. Okay. Let's see. So, I mean, this is 130 degrees back here. This is 112 degrees here. Just finding everything I can. Okay. So you see a big triangle there that we're trying to find a side of, and we're trying to find an angle of. So we might think, well, let's try law of sines or something first. So sine of angle. So this angle is 118 degrees over AC, which is one thing to try to find, equals sine of angle ACB over 50 equals sine of angle, let's see, what's this angle? CAB, I guess we call it CAB over 100. So that's my law of sines. Now, can I use that to find any of the missing things? Are there any two pairs where there's only one thing unknown? Do we have at least one pair where everything's known? No. We got to do law of cosines, okay? So we're going to use law of cosines. We could use it. I mean, there's a variety of ways to do it, but we could use it to find this side right here, or we could use it to find the angle first. But I'm going to go and go with the side just for, So if we're trying to find this side right here, then we want to use the angle across from it. So that works with law of cosines because we actually know the angle across from it. Because remember, So I'm going to write AC squared equals 50 squared plus 100 squared minus 2 times 50 times 100 cosine of the angle 118. That's opposite that side. Remember, these have to be across from each other. So then AC squared equals, you have a calculator, so you could use it, or 50 squared would be 25 with 2 zeros. 100 squared would be 1 with 4 zeros, minus, that's 100 times 100, so that's also going to be 1 with 4 zeros after it. Cosine of 118, I'm definitely leaving. So AC squared equals, we add 2,500 of that would be 12500. Now you cannot subtract this 10,000 from that. That would violate order of operations. So we're going to take the square root of both sides, plus or minus. We're going to go with the plus this time, but I want you to always write plus or minus because algebraically that's true. Sometimes we take the negative, sometimes we take the positive, sometimes we take both. In this case, we're only going to take the positive. That's a decision we can make after the fact. So that's the exact answer right there, by the way. I mean, we could write that. Okay, so that's the exact answer, which I'd like to see. We shouldn't have any decimals yet. No, just carefully. So 131.1286225. So we're going to go with 131.128. The units are miles. You need to put the units. Without the units, you're losing points. Now that's truncated, rounded to be 131.129 miles. Now, I went ahead and wrote these extra decimals just in case I'm going to use it, which I think I am, to help me find angle ACB. That's the other angle we're looking for, right? We're looking for that and that. So now we found that, so we could plug that in up here. And then we could use we could use law of sines. Now you got to be careful here. Remember, we would want to find the smaller angle of these two angles first. Now we're actually okay on this one finding either one first because we know this angle's obtuse. The only reason we do that is just in case the biggest angle's obtuse. This is the biggest angle, so you should be safe anyways. But the angle we're looking for is the smallest angle anyway, so it works out pretty nice. So I'm going to say, okay, well, angle ACB equals 50 times sine of 118 over, so I'm multiplying by 50, over 131.1286225. You better have more than 3 decimals in this work right here. If you don't and it works out fine, I'm still taking off points because you got lucky. Sometimes it'll work out okay. Sometimes it won't. We're not going to leave it up to chance. If you do and you get it right, I'm taking off points as if it came out wrong anyways. So that should be it. I think I made a mistake though. Let's see. Big mistake. Inverse sine. I'm trying to find this angle that's inside a sine, right? So I solved that, but then I got to take inverse sine. So it's got to be inverse sine of what I just found. So I'm going to go ahead and take advantage of what I just did. Inverse sine. I mean, that seemed really weird for an angle to be that tiny. So that kind of made me second guess. Now, since we're done, I mean, we could write a couple extra decimals, but measure angle ACB is 19.674 degrees. Round truncated comes out the same. So something like that. There are other ways you could have done that problem. I think we could have found the angle first and then the side from it. And I think that would have worked. Okay, got a little arc length circumference action here. Circle C and arc AB are both centered at C. If the length of AB is 100 miles and circle C has a circumference of 120 miles and AD equals 40 miles, then find the angle ACB. This is what we're trying to find right here. So we know how to find the arc length. So we know that arc length S, or, we know that theta over 360 degrees. And I think we're okay. We're going for degrees here. I mean, you could do theta. You could also do theta over 2 pi radians, and then you get the radian angle. But we're going to go ahead and go with degrees here. Equals arc length over circumference 2 pi r equals area, which we haven't really been using, but maybe at some future point. Area of the sector, which is that piece of pie, equals the area over the area circle pi r squared. So I think we're going to use this right here, right? And so we got to somehow use this arc length to help us find this angle, which I think we will be able to. But we need the circumference of the big circle that this arc would be associated with. That's not the circumference we have. So we can't just put, it's not that easy. If it was that easy, it'd be done so quick, you should be suspicious. So I think we got to use this to we got to figure out what this radius is. Okay. Now to figure out this radius, we need to figure out this radius. So I'm going to call this big R and this little r. So we got to find little r to find big R. And then we just add 40 to it. And then we can find that big circumference. Now we have the circumference of a little circle, which will help us find little r. So circumference equals 2 pi r equals 120. Then little r equals 120 over 2 pi equals 60 over pi. So that's little r. So it means big R, which is little r plus 40. I think it's really good to label all this stuff. Label stuff on your picture with variable names. I'm going to call this X. Show your work here. Show your thought process. Okay, so that's big R. So then if I use this equation here, theta over 360 degrees equals arc length over circumference equals 2 pi. Big R is the one we're looking for. So that means that theta equals the arc length 100 over the circumference of the big circle, which is 2 pi, and big R is 60 plus 40, times 360 degrees. That's our answer pretty much right there. I mean, that's pretty good. We got an answer. I do want you to go ahead and give me a decimal. We could potentially clean this up. I'm not saying you have to. If you did try to clean it up, we'd have 36 with 3 zeros on the top up here. You could distribute this. The pi's would cancel on the first one and get 120. The second one, you still have the pi, 80 pi. So it's a little cleaner version. I mean, we can keep going, but it's not necessary. But let's do 36,000 divided by parentheses 120 plus 80 pi is 96.949. Round or truncated. These are degrees. So this is measure angle ACB. There you go. That's it. Round truncated. So you got to be able to work with multiple circles. We call those concentric circles. You got to be able to do arc length, circumference, central angle stuff. Okay. Now, last problem is a sine regression problem. I'm promising you one of these. And so, but just one with several questions. Any of the kinds of questions we asked, are fair game. So the first thing to do is to get this information in here. So stat edit. I'm going to clear these lists and enter this information: 7, 10, 13, 16, 19, 2.4, 0.7, 3.2, 6.3, 2.6, double, triple check them. One little mistake's going to throw everything off. Okay, good. Now we go back to stat, we go to calc, bottom of the list, sine reg. Now, if they're in list 1, list 2, you could just enter, or you could always type them in. Second, number 1, L1, comma, second, number 2, L2. It does the same thing. It'll automatically pick L1, L2. We're going to write this down, okay? So sine reg, you got to write all this down. Y equals A times sine of BX plus C plus D. A equals 2.834964799. I want all the numbers. I might have to check your work. And the only way you're going to get credit is if I actually can put as close to what your calculator had in as possible and recalculate the answers. So I want all these numbers. It's one time. You can do it. Okay? There's really not that much work you have to show on these problems because your calculator's doing most of it. Okay? So get that written down. Let's get this into our calculator. Go to the Y menu. Go vars, number 5, statistics, equation, reg equation. Paste it in there very nicely. Go to window. This is time, hours in a day, 0 to 24. This is height of a tide. I mean, you could try and estimate here. Well, maybe it's -1 to like 8. Oops, I messed something up. -1 to 8. You just try that. Graph it. Now, if you get something that doesn't look very much like a sine curve, then you're probably in degree mode, which is what we've been in for most of this test. So go back, change your rating mode. You don't have to change anything else. Just hit graph again. Everything's good. That's the good news. So that looks a little better. I'm going to draw a sketch of this. I need a sketch, and you're going to label some stuff on it. So it doesn't need to be perfect, but just 0 to 24, label your axes. So that looks pretty good. Okay, times during the day when the tide is at least 4 feet. So we're going to go back to Y and we're going to enter in 4 feet, graph it. Okay, so then I'm going to make sure that seems kind of obvious. So at least 4 feet means greater than or equal to. So that's solid dot, and greater than. So I'm actually showing you my answer right here. This is my answer. Now I got to find those intersections. Okay. So second, calculate, number 5, intersect, first curve, second curve. I'll type 1 in to get this first one over here. So that is 1.1228864. And we'll do that one. Second calculate, number 5, intersect, first curve, second curve. We can move this over here, get closer to that. That is 5.9958366, comma 4. And then we'll do it again. Second calculate, number 5, intersect, first curve, second curve. And get over here. That is 13.300842, comma 4. And then the last one, second calculate, number 5, first curve, second curve. And that is 18.173792, comma 4. Okay, so the answer is, in interval notation, of course, bracket 1.122, comma 5.995. Now, if you rounded to be 1.123 and 5.996, union bracket 13.300, comma 18.173. And you got to give me units. These are hours of the day. Okay. You could have rounded and it would have given you different answers here. Okay, so that's what you do. Average tide from 2 to 8. Now 2 to 8, what we're going to do is this is the way you find the average of a function, is you integrate it to find the area under it. So 2 to 8, this is 0 to 24, so it's 12. So like 2 to 8 is kind of like, I don't know, something like that. So we're going to find that area. And we're going to smooth it out into rectangle and divide by the base of the rectangle. Or another way of thinking is we're going to accumulate all the hours from we're going to accumulate all the tide from 2 to 8 and then divide by the number of hours to get the average. So second calculate, you can do that from the screen if you want. 2 to 8 shades it. Okay. And the answer is 26.839776. And then we're going to divide by 6. And you get 4.473295. So the answer is 4.473. Round truncated comes out the same. What are the units? This is average tide height, feet. I need to see the setup when we're doing integration. Okay, times that the day the tide is increasing most rapidly. So when is the slope steepest? Here, and it probably happens like over here or over here. It looks like maybe over here, maybe over here. We'll see. We'll try. But there's 2 places now. That's max derivative. So what we want to do is we want to graph the derivative. So this is the original graph. We already have a basic idea of things that are going to happen. That's a 0 slope, right? Flat slope. That's a 0 slope. That's a 0 slope. That's a 0 slope. And then this should be a valley. And this should be a peak. This should be a valley. So it looks something like that. And we're looking for these max positive slopes. So there and maybe over here. We'll figure it out. So we're going to go to y equals, I'm going to turn this, we could keep it on. I'm going to get rid of this guy. I'm going to go down the bottom and maybe have this stored. If not, type it back in. The equation I'm doing is y1. I turn it on. Okay, turn it on. We could graph both of them. Now, it's likely that the graph we're interested in is going to look really small compared to this and maybe even be cut off. Yeah, well, but it's going to get cut off down here. But that's the graph we're interested in. So that kind of looks like what I was sketching, right? And so that's the peak we're looking for. And it looks like we might get another peak here. We'll confirm. They should be the same value. Okay, I'll almost get one here, but I think it's right there, right? So I'm going to go back to y equals, turn this guy off, do zoom fit. And then that'll just focus on the derivative graph. It takes a little extra time, but there it is. And so we think there might be a peak there, and there's definitely a peak there. And so we're going to use the calculator to find the maximum of this function. We're tricking the calculator, graphing the derivative. Those also, by the way, correspond to inflection points of the original graph. So you can calculate max. Now left bound, we're so close to where I'm looking at that I'm just going to use the cursor. So we'll let it find it. Should be right there. Okay, so this is 12.692808, comma 1.46266929. And then the other one, second calculate maximum. It should give you the same value as the last one. It looks like it's really close to 0. I'm going to say left bound 0, right bound 2, guess 1. Oh, shoot. I don't know if I did it right. Let's see. That seems right. Let's see. So it's saying that it's 0.5148718.5, comma 1.46266929. Now, if it truly is the same as this, these numbers should be the same, and they are. So that's good. So our answer, we're going to write very nicely, is we're going to say the times a day when the tide was increasing. The tide was increasing most rapidly at a rate of, so tell me the rate, and that's the y value of the derivative graph, 1.462. What are the units of that? Feet per hour should be two different units. It's a rate. At times t equals 0.514 and t equals 12.692 hours. Units. Very thorough answer. This is what I want you to write. You could have rounded these, by the way. I'm not going to write those answers down right now, but if that's what you want to do, go back and this would be 12.693. This would have been 0.515. This would have been 1.463 if you rounded. They all end up changing if you rounded, but that's it. So that's the calculator portion, and it's not necessarily, anyways. So there you go.